Good morning and welcome to Learning to Deploy Computational Storage with your friends here at ScaleFlux. You may have noticed that I look a little different than my profile photo. I'm not Matt. I am JB Baker, the VP of Product Management. I'm filling in for Matt, who was called away to customer meetings. So today we're going to go through, I'm just going to level set up front a little bit with what is computational storage, quick reminder, and go through some of the terminology that we're going to use. Then jump right into the demos of how you're going to configure extended capacity, kind of talk through the utilization, performance, endurance interactions as you make your choices and how much of the capacity you utilize, and then demo how you can set up or how the capacity utilization plays out in the drives. And then we'll move into Q&A. So just quick reminder up front, for computational storage, you can always go to SNIA.org for the official definition, but a computational storage drive, which is what ScaleFlux is focused on, integrates compute capabilities directly into the drive. This is offloading some work from the CPU and the host DRAM, performing that work right down in the drive with the intent to improve overall system efficiency. This is all about getting more out of your IT spend, getting more out of your power budget. So getting more capacity, more performance, more endurance or lifespan, and more uptime, or as you might be more focused on, less downtime through fewer points of failure. And then where can you deploy computational storage? Well, a CSD is at its heart an NVMe SSD. So you just plug it in anywhere physically that you would use an NVMe SSD today. We deploy or we sell the U.2 form factor right now. E1S, E3 are coming in the future. In terms of use cases, we see relational databases, OLTP, hybrid transactional analytical processing databases, and anywhere where performance, high performance, low latency, or local storage capacity is important for your efficiency. Other drivers that we see, and we're going to talk about a little bit here, are enabling you to use or to set a higher utilization rate for your storage. And that goes back to those benefits of getting more out of your dollar. So just to level set on some of the terms that we might use here in the demos, general storage and SSD terms to think about are going to be like capacity utilization and fill rate. This is what percent of the storage capacity that you have physically in the drives that you use before you're saying, hey, you know what, I don't want to fill this drive anymore. I'm going to deploy more storage or write elsewhere. Write amplification. This is an SSD term about the amount of data that's actually written to the drive for every gigabyte of data that's sent from the host. I'll draw this up for you in a couple of minutes. Namespace is an NVMe term, and this is effectively a logical partition on your NVMe SSD. And then other terms that are going to be more specific to computational storage here are extended capacity or capacity multiplier, as we refer to it on the marketing side. And this is formatting the drive to a logical capacity that exceeds its user capacity, or being able to store more data than the physical amount of NAND on the drive. And then thin provision namespace or extended namespace ties right back into that extended capacity. This is a namespace that has a larger logical capacity than the physical capacity that is set up behind it. That is, namespace size is greater than namespace capacity in the NVMe terminology. And then we talk about transparent compression in the drives. And this is data compression that's happening without the host or the application needing to take any action to initiate or trigger the compression. The compression is going to happen automatically as the data gets sent to the drive. Our controller is going to then compress the data before it writes to the NAND and then decompress on a read. So all that happens automatically. There's no integration, substitution of libraries, modifications to the OS, modifications to the application, or commands from the user to make this happen. And hence, we consider that transparent. And then we're also going to mention IT infrastructure management and monitoring tools. These are server, storage, networking, monitoring and management tools like Nagios and Prometheus that allow you to allocate resources and track how your infrastructure is performing. Okay, so that's it for the intro. Now, hopefully this will go smoothly of going to Matt's recorded demo of how you're going to configure extended capacity or a thin provision namespace. So go ahead with the demo.
Hello. So as we can see on our screen, we've got a 3.84 terabyte device installed in the server, and it's presenting a namespace that's 1-to-1, so 3.84 terabytes. Imagine if we had a data set that had a high degree of compression, so maybe a 3-to-1 or higher. We could actually make this 3.84 look like an 11.5, and I'm going to run you through that process now. So the first thing we want to do is actually delete the namespace, and I've got some pre-work that I already did here, so I can issue an NVMe command to delete the namespace. And then I need to create the new one. And now this is the create command. You can see the n size is much bigger than the n cap. The n cap is the physical size of the device, and the n size is the number of sectors that we want in our thinly provisioned namespace. So I'm going to go ahead and do that. And then I'm going to attach the namespace. NVMe command to attach. And then I'm going to rescan. And then I'm going to run SFX status again. I could use the NVMe list command, but this works just gives us a bit more data. And now you can see that my 3.84 physical has been extended to present itself as an 11.5 terabyte device. And so we could now create a file system, mount it up, and start using it with our data.
ScaleFlux embeds intelligent.
Okay, so you can see that, I mean, in how quick that was to do, it's very simple to set up the drive into extended capacity mode or thin provision namespace. Very straightforward. It's all standardized commands out of the NVMe command set. Now, once you've got it set up, you do have to start monitoring an extra parameter. This is like the one change in your process potentially. Because now that you've set up a namespace or in your file system that is larger than the physical capacity of the drive, you do have to start monitoring the namespace usage, which is what portion of the physical capacity that's assigned to that namespace is being used. So that's in addition to managing or monitoring the free space in your file system. So now let's talk about the capacity utilization, since we've extended the capacity here. ScaleFlux, we ran a couple of polls earlier this year on this topic. And what we found was that over 60% of the respondents said they only set their capacity utilization to 70% or even lower. And that means that if you set it to 70%, that means for every gigabyte of data that you're storing, you're having to actually deploy 1.4 gigabytes of capacity. So you're paying an extra 40% per gigabyte of data that you want to store, because you're reserving that 30% of free space for to address the concerns that in the second poll, 68% of respondents noted concerns about performance, about reliability, and about endurance as the key drivers for establishing these fill rates. Now, look, we absolutely agree that those are valid concerns. There's a very tight interaction between utilization or utilization rate, performance, and endurance. So I'm going to try to draw this out for you, and hopefully this will work okay, to explain this relationship. Wrong tool. Okay. So these are pretty well established curves. You can look these up in papers. I presented them before. So on the y-axis here, we have write amplification. On the x-axis, over provisioning, or how much free space the drive has set aside in itself. But this is going to align to overall utilization as well. So what we see is when you have a very low free space, the write amplification is very high. And this is like a asymptotic curve. And there's a few key points that I'm going to spot out here, and excuse my lack of doing this to scale. The first one here is at 7% OP, the second one at 28%, and the third one at 100%. So I'm choosing these because 7% OP lines up pretty well with what you're going to see with most of the one drive write per day class drives out there. And at this point, it's kind of a kink in the curve where you go lower than this and the write amp really starts to go crazy. But here, write amps are going to be around 4.5. So for every gigabyte of data you write to the drive, the NAND is going to see 4.5 gigabytes of data written over its lifetime as it moves the data around and does garbage collection. At 28%, this lines up pretty well with your 3 drive write per day class drives. And here, your write amp is going to be somewhere 2 to 2.5, depends on the drive. Out at 100% OP, there's always free space to write to, and the write amp is going to be about 1. Won't be exactly 1, but a little bit over 1. Now, this ties directly into your performance and endurance. And I'm going to draw the opposite graph here, the mirror image. And in this red line, what we see is this is your write performance and also your endurance with my lovely chicken scratch handwriting. And it's really the mirror image there. So the higher your write amp, the worse your write performance is going to be because the drive is writing more on the back end versus what you're trying to send from the host. And then the worse your endurance is going to be. Because for every gigabyte of data, you're consuming more of the lifetime of the NAND. Now, what is the relationship in terms of utilization rate? Well, on the y-axis, we can kind of look at this. If we flip what's low and what's high, and we think about utilization rate of the physical capacity, when you're at about 50% utilization, that's when you're at 100% OP. So you've used 50% of the drive and you have 50% free, 100% extra space. As you move down or move up in your utilization, now you're moving down on this curve on write performance, and you're going to start to crater your write performance. So so all those concerns about endurance, performance, reliability as you increase utilization are true. But when we start to do compression in the drive, what you see is that we're able to maintain that high performance and better endurance even at very high utilization rates. And now that I've explained that in theory, we're going to show you the demo of this running in reality on a ScaleFlex drive and another NVMe SSD. So go ahead with the second demo.
So now we can see here a system with 2 SSDs in it. One of them is a ScaleFlux CSD 3000 mounted under the MediaPoint CSD 3K, and the other one is a well-known enterprise write-intensive SSD mounted under Media Other SSD. And you can see that there's quite a lot of data on both of them. They're similar in size, not quite the same, but their file systems, which are XFS, are full to over 95%. What I'm going to do now is run a FIO command to give some exercise to the system. So the first one we'll do is we'll take a run at the CSD 3K, and we're going to write 4K blocks, 4 jobs, 128 queue depth across 4 25 gig files for 60 seconds. So you can see this spinning up as it moves past its initial load. It's hovering around the 600, 690, 700K in that sort of range. So the drive's doing quite a lot of work at this point to deal with those inbound IOPS. Now, what I would notice is both of these devices are Gen 4 capable. Unfortunately, my test system is a Gen 3 PCI system. So this is not the maximum performance the devices can give, but it's a good indication of comparative performance between the two when the file systems are very full. So it's just about to finish, 10 seconds to run. Okay, so you can see that we got 687,000 IOPS on average, and you can see that the average completion time is around 749 microseconds shown here. So let's run the next test on the other SSD. So you can see exactly the same string, and we're going to run on the other SSD now. And again, you can see already that the performance is quite different. The other device, very full, is having to do a lot of garbage collection, a lot of maintenance internally. So that really does affect performance. And at the moment, we're seeing around half the amount of IOPS on that other enterprise write-intensive device. And again, just coming into the end, and we'll let that finish. So again, you can see this time many less IOPS, 220 with about 800 megabytes of bandwidth. And then let's look at the average completion time is quite considerably different. That slower device, that slower response time. So all in all, what's this showing is this is showing that when we use a scale flux device, even with a small amount of compression in the data set, we can fill the device and utilize the volume, the capacity of the device to a much higher extent compared with other enterprise write-intensive SSDs.
Okay, so as Matt just demonstrated, you can get significantly higher throughput. It was about 3 times the write IOPS at about 1/3 of the latency by having that CSD compression right in the drive, even at a very high utilization rate of the storage. So that's a key way to mitigate all of those concerns that were mentioned in the response about write performance, endurance, reliability, application performance. Now, we also did promise in our abstract to talk about endurance. A demo on endurance is going to take longer than we have time for in this video. We're gonna work up some kind of time lapse version of that because it can take weeks to kind of show the absolute impact there. But as I drew on the whiteboard there, there is that interaction of write amplification and utilization of the NAND. And as we compress the data, not only do we reduce the amount of data that's written initially, say a 2-to-1 compression ratio goes from 2 gigabytes of data down to 1 gigabyte of data on that hot write, but we reduce that write amplification on the back end or the cold writes that happen with garbage collection. So we'll follow up with a short video on that later. All right, so this all should look pretty easy. And if you're curious about how to evaluate computational storage for your use case and what other considerations you might take into your thought process, you do start to need to look at being selective in what SSD you choose. And a lot of people will just take whatever SSD is delivered by the OEM. All SSDs are fast, right? But as we just showed, that's not really true anymore. And then what complexity is this going to add to your system? Hopefully we showed you here that it's actually pretty simple to configure and pretty simple to deploy. We have had feedback from customers who have deployed the extended capacity and said once they got over their initial fears in that first meeting and got to deploying it, they found it was actually very easy to integrate into their server management. And we do actually offer plugins for Nagios and Prometheus. If you have another management tool, you can work with us, and we may be able to provide a plugin for that as well. And just do realize that your choice of SSD can really impact the overall ROI of your data center. With that reduction in write amplification, you can get significantly better life out of your SSDs, potentially extending the life of some of your infrastructure beyond the 3 to 5 years, out into the 7 years as you start to support some of your other initiatives. You may have initiatives around sustainability or power efficiency or modernizing your database overall, or how much space do you consume to deliver on your workloads. In order to test this in your environment, you can reach out to us at scaleflux.com or hit us up on LinkedIn, and we'll be happy to discuss with you further. With that, I will open up for Q&A. Okay, how do I know what to set the drive to, or how compressible is my data? All right, this is we get this one all the time. So it's pretty easy to estimate how compressible your data is. There's a couple of different ways. You could just take a sample of your data set and run it through gzip, and that's going to give you a pretty good estimation of what you would see with the ScaleFlux drive. Also, we do have a tool that we can send to you that you can, again, run a sample of your data set. You're not sharing it with us. You're keeping it on-prem to then see what the compressibility of the data is. And then just in general, what we have seen, the feedback we get is that on those databases, the typical compression ratio people are seeing is anywhere from 2 to 5 to 1. So extending capacity to 2x to 3x, people have been very, very comfortable with. What do I need to do to install the drives? Is there a ScaleFlux driver? No, there is not a ScaleFlux driver. On our prior generations of product that were FPGA based, we did have a ScaleFlux driver. But in the 3000 and beyond, we are on a ScaleFlux designed ASIC. And with that, we transitioned to using the inbox NVMe drivers. So there is no software to install. There is no driver to install to use the ScaleFlux drive. You plug it in and it gets recognized as an NVMe SSD. If I want to reformat the drive to a different capacity, how do I do that? First, you take a drink so you can continue talking. Well, as Matt showed, you're going to do, or you're going to create a new namespace. And so all of this is going to be managed under the standard NVMe commands. You will have to delete the namespace or remove the namespace that you have existing. So you're going to want to migrate your data off of the drive before you reformat the drive. And then just create a new namespace or multiple new namespaces to the desired capacity. And just to reiterate, that is not any different than you would have to do with another NVMe SSD. What happens to my data if I run out of physical space? Good question. And we've had some people intentionally try to break things. But this is where you absolutely need to be monitoring the namespace capacity or end-use command, end-use data on your drive so that you avoid running out of space in your server management. We do have a couple of options for you on that where we throttle the performance of the drive near its full so that you don't get a surprise there. And we can dip into the over provisioning to protect you from running over by a little bit so that you can still issue commands to reclaim space and clear out the drive. Do all drives need to be configured the same? Can I mix and match? Yeah, you can absolutely configure drives to different capacities. The ScaleFlex drives can be, each one that you have deployed, you can configure to a different capacity, and you can mix and match ScaleFlex drive with drives with other vendors' drives. How do I not run off the road? Well, that's kind of the same question of how do I avoid running out of space. You do need to be monitoring that end use feature or attribute on your drive. If one of my drives fails and I have to swap it, how do I know what configuration to use if extended capacity was enabled? Well, you're going to have to rely upon what data you have or what information you have in your file system about how big that how big of a namespace you had created on that drive. So when you install a new drive, if it's a ScaleFlex drive, then you want to at least configure it to the same capacity point. Or if you're buying another vendor's drive for some reason, you'll need to buy at least enough capacity to match that overall namespace. So you may have to buy a bigger drive. Okay, if you have additional questions, please add them into the chat. All right, well, if we don't have another question in the next minute or two, then we'll wrap it up. And I do encourage you to visit us on scaleflex.com, where we have additional information about the drives. We have many other resources on how to use and configure the capacity. So we have a nice white paper that was written up by our Senior Director of Technical Marketing. All right, well, thank you for joining us this morning, and have a great day.